First of the two joint speakers, loves reading so much, she's a member of 4 book clubs. How do you keep up with that? We'll have to find out. Our other speaker loves the Flintstones, and her favorite character is Betty Rubble. So everyone, please welcome Danielle and Selen to the stage.
Hi, everyone. Thanks for the opportunity to share our experience of using art and data science techniques in government. My name is Danielle Larese, and I will be presenting with my colleague, Selen Stromgren. The title of our presentation is Finding Waldo, our supported transformation of unwieldy data into information. We work at the U.S. Food and Drug Administration, FDA, Office of Regulatory Affairs. And I also wanted to say that Selen and I are both chemists, so we have scientific backgrounds and definitely not data science. But here we go. My second disclaimer is that everything we present represents the views of the speakers and should not be construed to represent FDA's views or policies. The Office of Regulatory Affairs, or ORA, is the second largest group by the number of full-time employees within the FDA, as we can see from the left chart. Only the Center for Drugs is bigger. I think there's feedback. Is your mic on? Okay. Right, the middle chart here shows the breakdown of ORA staff into inspectional, investigational, and scientific and labs. The split is about 80% inspectional and 20% labs. We think of ORA as the place in FDA where the rubber hits the road because the office is comprised of people who are out, traveling to firms, doing inspections, gathering samples, and analyzing those samples. In this presentation, we're going to focus on the laboratory and scientific network of ORA, which has roughly 900 staff and which includes 12 laboratory locations around the contiguous United States, plus Puerto Rico. So this is who we're talking about, these regulatory labs and their scientific enterprise. So I'm happy to report that there is R in FDA. In fact, there are 2 R's in Food and Drug Administration when you spell it out. Anyway, our studio is available to all of FDA staff because it's an excellent tool that allows sophisticated data trending, analysis, organization, visualization, and automation of workflows such as our Shiny interfaces. We found that R can be popular even for those not previously trained in programming due to its open access structure, ease of use via availability of packages, the availability of the online community support, and the existence of specific use groups and communities, even at the agency, to foster collaboration, cross-use of applications, and joint troubleshooting. But there's a shift in the professional landscape at the agency with an emphasis on hiring in multidisciplinary areas. So titles like chemist, microbiologist, and engineer are kind of becoming things of the past and getting replaced by data scientists, pharmaceutical engineers, and artificial intelligence architects. There's also a new community launched by the FDA's Office of Digital Transformation called Data Forward that uses R as a platform to train a pilot cohort in data science techniques. So how do data science and R mesh with ORA? ORA scope intersects with all FDA regulated centers and regulated products, which means that ORA labs work with all these product types listed. Since these product types are so diverse, we get these 2 statistics at the bottom. The FDA regulated products account for about 20 cents of every dollar spent by US consumers and account for about $2.7 trillion in annual consumption. So this helps convey the vast swath of consumer products that ORA interacts with. But we also want to be clear that ORA does not write or develop any policies or regulations. Our mission takes place post-market, that is after products are being marketed to the public. So this sounds like an awful lot of work, but let's think about what data it generates since we're here to talk about data science. So ORA has a vast amount of data that relates directly to the agency's public health mission. And there's a bunch of examples such as facility inspection reports, enforcement activities, outbreak and adverse events and the reports thereof, laboratory results, sample collections, and it goes on. In addition to this data that's directly generated from our public health mission, ORA has operational data such as training records or internal proficiency records and regulatory lab sample turnaround times. But like many fine people before us, we find ourselves with all this data, but with issues as well. So most of our data is available, but not accessible in the way that we would want it to be. So most data, especially the type of data that's acquired over time and under changing parameters, exists in a format that does not lend itself to easy extraction of key information and trends. And further, human brains are not wired to reliably build cumulative understanding of a data set acquired over time. The last data point gets the most attention if there's a need to make a particular decision at a given time. And this issue leads to the impulse to reacquire new data rather than leveraging the existing data that you have. So sometimes it'll feel easier to reacquire new data to address a specific need rather than to distill the existing data in an effective way to get more robust and historical information. But the point here is that reacquiring is in most cases not the best option. And often for government agencies, this can manifest as contracting and hiring third-party contractors to do this work for us. So further, a reliance on outside expertise of contractors extends from the activation barrier of not having a data proficient workforce. So within the agency, there's an urgent need to become proficient in tools such as R, which could in turn help us deploy these data science techniques to master our existing data. And a data-driven approach could transform the historical practice of policymaking based on anecdotal and qualitative information into a much more robust approach where objective and wholesome evaluations can illuminate the right actions and decisions. So I'm going to turn over to Selen to discuss some case studies that we've done.
Thank you, Danielle. Okay. Now we would like to illustrate a use case for a systematic data science approach. Our example involves data in the form of laboratory exercises acquired over. Each exercise is basically an application of a scientific method by each laboratory in our network to detect unknown analytes in samples that represent FDA-regulated products. So this could be pesticides in fresh produce, for instance. These exercises show that the labs are able to run scientific methods proficiently to obtain accurate results. There are several exercises provided to the lab network per year, and the results of each exercise are captured in memos distributed to senior managers, who have to, of course, keep an eye on quality operations of the laboratories. In this format, the recipient understanding of data is unsurprisingly disjointed, distracted, high-level, case-specific, and certainly not memorable. If there's an interesting trend or revelation, aka Waldo, hiding in the data, it will almost always be missed. In the early days, memos were being mailed to the recipients. As email became routine way of doing business, the memos started being transmitted as attachments to emails that hit the rather cluttered inboxes of the managers at random days and times of the year. As can be expected, mere digitization did not make the data more accessible nor noticeable to the managers. Via our pilot project, we wanted to explore a way to look at the data in an aggregate format. One powerful visual that the user can interact with to see patterns and trends over years across labs and through different exercises. For our pilot project, we concentrated on 5 years of data that represented 100,000 data points in 300 separate reports. This slide shows how the data in PDF files were transformed into a matrix format that easily lends itself to further manipulation and visualization through various data science tools. This dashboard is interactive for easy access, transparency, relational observation, and trend analysis. So was there a trend or a pattern hiding in our data that became visible when one looked at the totality of information in a structured way? Was there a Waldo hiding in our data? There indeed was a Waldo that we uncovered in our cobwebby data of 5 years. Trends in reported findings led to an investigation that uncovered a practice used by some laboratories that caused a reagent to sit too long on the bench, leading to slight evaporation of the solvent, which in turn led to slight overestimation of concentration of the proficiency samples. The workflow was modified, and all the labs using the defective workflow attained much tighter standard deviations on their measurements. In this instance, the methodology was fine, but handling during method steps needed to be modified. So we were indeed able to find the Waldo, or at least one of the Waldos, that was hiding in this busy data. So what are some other applications of R that we decided to look into? So in addition to systematically looking at big data, we also use visualization in R to assess impact from our scientific activities to inform future investment decisions. Data visualization also helps us understand evolution of our research landscape. Trends from year to year provide insight into laboratory principal investigator activity in research, publication frequency, stratification of projects among different regulated areas, the evolving expertise and proficiency of our workforce, productivity in our organization, and connectedness and collaboration of our laboratory network. Since research impact is a hard to quantify concept, we've come up with some evaluative metrics in order to assess return on investment from our scientific activities. This slide shows the buckets of metrics we use to understand impact. And here the different font sizes represent the amount of output in each impact bucket. These metrics try to go beyond mere bibliometrics and try to get at more nuanced outputs, such as whether the research led to a method that was used in a coordinated agency response to an emergency, whether the research stimulated diversification and modernization of our technology platform, whether the research increased our analytical readiness and preparedness to future public health events. This is an example of a chord diagram that we've generated using R that packs a lot of information. It shows the relative size of research activity in the various FDA-regulated areas and how much output each area of research has produced in our various impact buckets. So at a glance, you can immediately see we're very active in food-related research as opposed to pharmaceutical and tobacco and devices. Where do we want to go next with our utilization of R? We would like to advance our mastery of R to the point that we can start using clustering and other predictive relational models for product risk assessment, product profiling, post-market critical quality factor monitoring of FDA-regulated commodities. Being able to leverage such models would help us optimize our method parameters based on analyte matrix scope, perform risk assessment of incoming import items based on country of origin, package features, historical importer information, and identifying and classify contaminant profiles in typically consumed foods. Identifying patterns in our existing databases to inform future decisions will introduce operational efficiencies and allow FDA to focus its limited resources on the products and firms that pose the largest risk to consumer health and safety. To recap, our strategic goal is to expand the use of R at FDA or A to target products, optimize operations, and communicate harvested information. We'd like to build a workforce that is proficient in tools such as R so we can take charge of our data. FDA Data Forward, which was mentioned earlier, is part of the FDA lifelong learning platform and teaches basics of R to cohorts of students who are FDA employees. And Department of Human Health Services, HHS Data Collab is another training activity that just got launched. FDA is under Department of Health and Human and Health Services. And finally, we would like to continue mining and retaining historical data in a structured format and expanding our cumulatively increasing knowledge base to help with our investment decisions, operational decisions, risk assessment decisions, and response to emergency decisions. And that is the end of our talk, ahead of our time. And that's our contact information. And we'd love to answer any questions you may have during the breakout. Thank you for your attention.